we want to check if this is an ordinary point or a singular point. And if it's a singular point, we want to check if it's regular or not. So the thing to do is to divide out by the leading function and then get y double prime by itself. So the x squares are going to cancel in the y prime term, and then you have an x minus 2 over x squared in the y term. So the fact that it's x is equal to 0 is undefined for the q function, the capital Q function, means that we have a singular point. So our capital P of x is 1, which is analytic. Our capital Q of x is x over 2 over x squared, which is not analytic at 0. So we have a singular point. At x is equal to 0. So we want to see if this is a regular singular point. Well, the P of x we don't need to worry about, but we might need it later on. So P of x, little p of x, is x times capital P of x, which is just going to be x. And this will be more important for us when we try to find the roots for the indicial equation. So we might as well do the work. The little q of x is going to be x squared times capital Q of x, and that is going to essentially cancel out, right? The x squared. So it'll be x squared times x minus 2 over x squared, which is just x over x minus 2. And just for the sake of preparing it so that we can find the indicial equation, we would write it with a constant term first. So we see that this is analytic. And so we can conclude that this is a regular singular point. Which means that we can use Frobenius's theorem to solve for this differential equation. So Frobenius tells us our solution is going to depend on the indicial equation. So we should look for the indicial equation. And, oh, I forgot what that is now. R minus 1 plus A naught R minus B naught or plus B naught? Plus. So it's all pluses except for the R minus 1. So we know that A naught is equal to 0 and B naught is equal to 2 based on our little p and little q expansions. So then we can work this out. R squared minus R plus 0 minus 2 is equal to 0. R squared minus R minus 2 is equal to 0. I think this is factorable, right? R minus 2. Wait, which one of them is a minus? One is a plus. So we have the second case of our initial roots breakdown tells us that if the roots differ by an integer, then we have to take a look at what the form is. It has a specific form. What's kind of neat about this is that I was reading somewhere that if you have roots that are different, that differ by an integer like this, to start off with the smaller root first. So, well, maybe it's not so sad. So our solution should look like n goes from 0 to infinity according to Frobenius's theorem, c sub n x to the n plus r. But r in this case is -1 that we're going to try first. So it's going to be n to the r minus 1. Josh? Yes, it is. It's always going to be a constant term. It's because the capital P is 1, and then little p is x times capital P. And so little p of x is actually equal to x. So it would be 0 plus x, 1 times x, plus 0 times everything else is 0. All right. So our r that we're going to choose is -1. So let's rewrite y is equal to the sum n goes off to 0 to infinity of c sub n x to the n minus 1. Now, I don't know exactly what I did last time, but when you take the derivative of this, because we're talking about this as this isn't exactly a power series. I don't know if I think we might have mentioned that. It's not exactly an infinite polynomial because of the way the powers are set up, especially if you have fraction powers, or in this case, negative powers. If you have negative powers, and you kind of have to be careful about doing your derivative. And so I'm going to write my derivative still starting at 0, because we have to allow for this when n is equal to 0. And I'm going to take the derivative like I normally take the derivative. So it's n minus 1, c sub n, x to the n minus 2. And again, we have to allow for that, for the powers to be negative, to be fractions and stuff like that. And then that gets us our y double prime. Again, still starting at 0. N minus 1, n minus 2, c sub n, x to the n minus 3. So we have our first derivative or second derivative, our original function, and we're going to try to put it into this into the differential equation. So let's go ahead and do that. We have an x squared. We have a y double prime, and goes from 0 to infinity. N minus 1, n minus 2, c sub n, x to the n minus 3. And then we have another x squared, and goes from 0 to infinity of n minus 1, c sub n, x to the n minus 2. And then we have to distribute this, x minus 2, and goes from 0 to infinity, c sub n, x to the n minus 1. Don't know yet. Let's distribute everything and see how the powers are going to look like. So if we take this x squared into here, we're going to get n goes from 0 to infinity of n minus 1, n minus 2, c sub n, x. Now we have to add 2 to this, so it becomes n minus 1 power. And let's multiply this by x squared in here. We got c sub n, n minus 1, c sub n, then x to the n minus 2 plus 2, so that's just n. And then now let's multiply the x in, and goes from 0 to infinity, c sub n, x to the nth power, and then the last one, minus 2. Let's put a minus 2 in here, c sub n, x to the n minus 1. Yeah. Because we're allowing for the powers to be negative or fractions or stuff like that, so we kept it at 0. So before, when we're dealing with ordinary points, when n is equal to 0 and we take the derivative, the first term goes away anyways, and so that's why we have kind of methodically got rid of that 0th term and we start with 1. But for this, in these cases, because you have to worry about possibilities of the powers not being constants and not just totally disappearing, we want to keep it there. Was there a question? So, okay, let's combine. Am I interested? I think I might be interested in combining it into one, maybe. We could adjust, right? So we want everything to be at the same power, is what we really want. So we can have it to the n minus 1 power. If we have it to the n minus 1 power, we add 1 here. Is that how it goes? Or we want it to be the nth power, we subtract. Yeah, I think it's good to keep starting at 0. So let's, I think in general, what you want to do is you want to have it to the power of where you originally started. And so let's change this to, are we going to change to k again? So let's change it to k minus 1. So we're going to subtract 1 within here. So we're going to add 1 to the subscript. All right, let's see if we can manage that. We'll keep everything else the same, and we'll combine everything together when everything's together. K goes from 0 to infinity, and I'm going to switch to k's now. K minus 1, k minus 2, c sub k, x sub k minus 1. And now this is where I'll switch. I'll subtract 1, so this will be k minus 2, c sub k minus 1, x to the k minus 1. And so now my k starts with 1 to infinity. So I'm not changing the series here, I'm just changing the way it looks. So the third one is going to be c sub k minus 1, x to the k minus 1. And then the last one will remain the same. So now everything is of the form or of the power x to the k minus 1. The couple of series, it starts with a 0. We can take out the 0th term, and then everything else can be brought together into 1. So maybe I'll try to do that in one step. So over here, when k is equal to 0, I have negative 1 times negative 2 times c sub 0, x to the 0 minus 1. What? Well, let's just leave it like this for now. And then we'll take away this k is equal to 0 term from this one, because that's the other one that has a 0. And so that would be a negative 2 c sub 0 x to the negative 1. And then that's it, right? They cancel? Okay, I guess that's good. Now we'll put everything together. This time it starts with 1. And I will try to put the k minus the c sub k terms together, and then I'll try to put the k sub 1 terms, c sub k sub 1 terms together. All right, so the c sub k terms is going to be k minus 1, k minus 2, and then there's a minus 2 for the c sub k. And then the c sub k minus 1 terms, there's a k minus 2, and then a 1. Okay. So let's deal with this really quickly. If this whole thing is equal to 0, does it equal to 0? So the whole thing's equal to 0, which means c sub 1, that doesn't mean that c sub 1 is equal to 0, or c sub 0 is equal to 0. It means c sub 0 is still an arbitrary variable or arbitrary parameter. So we'll keep that arbitrary. So that just means there's no c sub 0 involved here, but when we write out our series, there will be c sub 0 there. Okay, so now let's deal with this in here and solve for c sub, I guess we should solve for c sub k. C sub k is equal to negative c sub, what is this? K minus 2 plus 1 is k minus 1. C sub k minus 1 negative, and divide by the coefficient here. Should I try to simplify it? Just k times k minus 3. So if we multiply this out, it'll be k squared minus 3k plus 2. and then the 2 would cancel with a minus 2. And so this is what you have. All right, so this is our pattern for k goes from 1 to, starts with 1, right? Starts with 1. All right, so let's see if we can continue on with this pattern. So k starts with 1. C sub 1 is equal to, what happens when this is 1? That's a negative. 1 minus 1 is 0, right? Yeah, sure. So C sub 1 is equal to 0. Let's take a look at C sub 2. K is equal to 2. C sub 2 is going to be negative 2 minus 1. C sub 2 minus 1 divided by 2 times what? Oh yeah, it's going to just be zeros. I don't know. When we put 1 in there? Oh, but it's C. The thing is that C sub 2 and then C sub 1 is equal to 0. Oh, shoot. Yeah, that would be a good idea, huh? Which is a power series that would be obtained from R is equal to 2. Well, I don't know. You want this for extra credit? What? You don't want this in your life at all? Yeah, I think there was an issue over here where if n was equal to, yeah, which means the first solution should have been the bigger one. Yeah. All right. Well, so this thing gave us a C sub 0 only solution of C sub 0 because everything else is 0. So your solution here, y sub 1, is going to be, according to this, what is it? N goes from 0 to infinity of C sub n x to the n minus 1. Let's put in the values of C sub 0, or n is equal to 0, n is equal to 1. So when n is equal to 1, this is a 0 power. N is equal to 2, etc. And then according to our result over here, we have all these terms here are all equal to 0. So we only have y sub 1 is equal to C sub 0 x to the negative 1 power. So this is one of our solutions. Now we should try to get the second solution by putting in the r is equal to 2. Let's see if this is enough room. We should go on another page. It could be, yeah. Who knows? Yeah. Yeah, I think so. So this is a different C0 here, right? Mm. Is there what? This is an ln. This is supposed to be a b. Boy, okay, here we go. So we're going to want to find its derivatives again. And this is going to give us, and goes from 0 to infinity. n plus 2 b sub n x to the n plus 1. And then the derivative of this, c sub 0. And then we have to do the product rule. Derivative of the first times the second. So 1 over ln x times ln x plus the first. 1 over x times the derivative of the second. Wait, the derivative of 1 over, no. Yeah. Negative, right? So it's the first term times derivative of the second 1 over x squared. So our solution, or how does this simplify? Simplifies c sub 0, 1 over x squared ln x plus 1 over x squared. And n is equal to 0, it'd still be okay here, right? So let's do the derivative, the set derivative of that. N goes from 0 to infinity, n plus 1, n plus 2, b sub n, x to the n, plus c sub 0. Let's see, derivative of the first, it's 1 over x cubed times the second, plus the first. Derivative of the second. And then the derivative of this, which is minus 1 over x cubed. So we got minus 1 over x cubed and minus 1 over, that's 2 over x cubed. What? Yeah, this whole thing is to set it equal to 0. Okay, well, we need to put that back into the differential equation and set the coefficients equal to 0. Yeah. Well, let's see. Well, Yeah, I don't know. All right, why don't we do this? Do you guys try to solve this for next time for extra credit? Let's see, how many points? 2 points. 2 points for the final. No. What? Next class. Not much time, but it's extra credit, so you don't have to do it. So what I'll do is I'll try to solve for this solution, try to come up with a neater solution, type it all up, and then show it to you guys or videotape it, and then just have the video available if you want to check that. So if you don't feel like doing this and you want to just see it done, we can do that. In terms of the exam, I think we'll stick with the ordinary points, solutions around ordinary points. I think that's going to be enough of enough work for you guys to do, anyways. But I think I still might ask you some theory questions on the singular points, like, you know, well, to say figure out your initial equations, and then how's your solution supposed to look like, something like that. All right, are you guys okay to leave this alone now? Let's move on. So this is your differential equation that you're going to solve for, and for those people that are interested. So good luck. So we should move on. Chapter 7. So a lot of these differential equations that we've been solving for have special techniques and stuff, and so we're gonna find another technique that we're gonna use to solve essentially the same differential equations that we've been solving, except there's going to be one special type of function that this particular differential equation can solve that none of the others can. And that's because it allows us to deal with a special kind of function. Chapter 7 is, what's chapter 7? Chapter 7 is Laplace Transforms. So the idea behind Laplace Transforms is kind of a way of skirting the solution to a differential equation by going to I like to think about it as going to another world. Um, so you're here in the real world. How should we denote the real world? I'll just say real world. So this is the real world up here. And the idea behind solving a differential equation is, in the real world, you would use calculus to solve for this differential equation. So what we're going to do is we're going to change worlds and go to another world, and let's call the other world the Laplace world. And what you're going to do is you're going to take your differential equation and transform it into another expression over here. Now, we're going to this Laplace world so that in the Laplace world, we don't have to use calculus. And so in the Laplace world, all you're going to do is algebra. The small caveat is that the algebra that you'll be doing in the Laplace world is partial fractions. Now, I don't know if you noticed, you learned partial fractions in Calc 2, but partial fractions is just algebra, right? You used it to help solve for integrals, which is calculus, but as you're doing the partial fractions, all you're doing is algebra. You're decomposing fractions. So instead of finding common denominators and putting fractions together, you're taking a big fraction and you're going to take it apart. That's all partial fractions is, but nevertheless, it's still algebra. And what happens in this process is that you're going to get a solution which we'll denote as capital Y of S. Now S is going to be our variable. S is going to be our variable while we're in the Laplace world, and we'll just keep t as our variable when we're in the real world. And so once you solve for this algebraically, you get to go back to the real world by bringing this solution, the y solution that you got, and make it as a function of t again. Now, clearly, there are these trips that you need to take to go to the Laplace world and back, and that requires some calculus. But once we establish the calculus for those things, then we're just going to use these formulas to take us to the Laplace world and to take us back to the real world. Okay? So the step that you take to go into the Laplace world is called the Laplace Transform. Yes? And then you'd have a system of equations? Yeah, I think so. So the means for getting to the Laplace transform world is called the Laplace transform, and then the means to get back to the real world is called the inverse Laplace transform. So we'll have notation for that. And the notation generally that we're going to use is that if we have a function to represent in the Laplace world, we'll represent it with a capital letter, either capital F or capital Y, and then we'll use lowercase letters for what's happening in the real world. Again, the S and the T, the different parameters. And so the symbol that we're going to be using is a fancy L, script L, to say we're taking the Laplace of something. And the inverse Laplace to take it back. Okay? All right. You ready to go Laplace world? Sure. So the Laplace transform is defined by an integral. An integral, an infinite integral, where S is going to be the new parameter or the new variable you're going to have. The T is the old parameter or the old variable that you have. And what that does is it transforms your little f function into a new capital F function. Again, the little f has a t in it. When you integrate with respect to t, the t is just a dummy variable and it goes away. And then all you have are variables, the variable s. Now this is an infinite integral, but we're pushing it down with an e to the negative st, which in the positive side shrinks it down. So we're hoping that we're actually going to get some finite results out of this. And what we're interested in doing is we're interested in finding out the Laplace transforms of some basic functions. Polynomials, sines and cosines and stuff like that, constants. So let's run some functions into this Laplace transform and see what we get. And once we get them, we'll just use them as our facts, and then we'll create a table of these Laplace transforms. So let's start off with something really simple. I don't know if this is simple, but that's the simplest we can get. When f of t is equal to 1, how is it going to go with our Laplace transform? So we're going to integrate an infinite integral e to the minus st, and then 1 times dt. Remember your antiderivative here of e to the negative st, where t is the variable. You do a U-substitution with the 1 over s, right? And then you have to do that limit thing too for the improper integral. So let's do it properly the first couple of times, and then we'll be a little bit more relaxed with the formal Calc 2 notation. You do a U-substitution, it'll be e to the negative st, and I have to divide out by a negative 1 over negative s or something like that. Is that right? And then at infinity is that limit, so we'll just call it b. And then we have the limit as b approaches infinity. We'll put b in there, so it's a negative e to the negative sb. Remember, the t is your variable if you want to put t equals 0 there. And because as b goes off to infinity, we have e to the negative infinity that goes to 0. And then we just have 1 over s, negative, negative, so that's a 1 over s. So what we could do is we can construct a table of Laplace transforms for ourselves as we do a few more of these, and then see if we can find a pattern maybe. Okay. All right, let's should we do another one? Should we do t? It's usually the thing to do. So this looks like it's going to require integration by parts. Right? So u, v, du, dv, u is equal to t, dv is equal to e to the negative st. And then v is going to be 1 over negative s. So I think it's going to be t times e to the negative st over s minus the integral of v du. V du is equal to 1. V is that. So be negative 1 over s squared e to the negative st over s squared. Not sure about the negative sign though. The negative? Minus, minus. I think it's a minus. So we're going to evaluate this from 0 to b and then take the limit. So we put limit as b approaches infinity. This is going to be b e to the minus sb over s minus e to the minus sb or s squared minus 0 minus 0 e to the 0, which is 1 over s squared. Okay. Looks like these things will go away as b goes off to infinity. We know that this goes off to infinity from last time. Now we have b times e to the negative sb. That's like saying b over e to the sb. You can do L'Hopital's rule or just try to remember that e is a function that goes to infinity faster than any polynomial. So this whole thing is going to go to 0. And then we're just going to have 1 over s squared. Yeah. Yeah. I mean, the way I did this integral is I took the parts, integration by parts. If you were to guess what t squared is going to look like, what do you think it'll look like? What? 1 over s cubed? It's close. So actually see the pattern, I guess it would be good to just do it one more time. We could just put it into the calculator. Let's just do t squared. Good. Let's just do it like this. So integral from 0 to infinity t squared e to the minus st dt. So for this one, I'm gonna do my U's and V's business. Forgot how I did it. T squared. And do I start off here or do I start off one level higher? Oh, you start off at the same level and just do diagonal. So this is 2t and 2, and then zeros for the rest. So that's, and this is negative 1 over s, e to the negative st, positive 1 over s squared, e to the negative st, and negative 1 over s cubed, e to the negative st. So, and I think they alternate signs, right? Plus, minus, plus. So what do we have here? We have limit as b approaches infinity of negative 1 over s t squared e to the negative st minus 1 over s squared times 2t e to the negative st, and then plus minus, so that's negative 1 over s cubed, and then 2 e to the negative st. This is not a Calc 2 class, I don't care. If we were in Calculus 2, then I would probably care a little bit more. But in any case, these things would all end up going to 0, and then the b part of this would go to 0. And so we'll end up having the limit as b approaches infinity of, well, let me write it out, 2e to the negative sb over s cubed, that's negative, and then negative, negative 1 over s cubed, 2 over s cubed, and e to the 0 power, which is just going to go away anyways. So there's a 2 that comes out. So the pattern didn't look like it was going to follow with just a bunch of 1s. And unfortunately, or fortunately, I don't know. Maybe there's no fortune here. When we do this for t cubed, we're going to get another weird constant over s and then 1 power higher. And so you can check if you do what these guys were talking about, do it for general n. You can check that your we could see that the denominator has s to 1 power bigger than the original one, right? But that constant, if you do these integration by parts several times, if you have a large n, like n is equal to 5, you imagine what happens in the integration by parts here. You'll get 5, and then 5 times 4, and then 5 times 4 times 3, and 5 times 4 times 3 times 2, etc. And so this actually comes up with a factorial. So we can have, and then this works, by the way, when n is equal to 0, that's 1. When n is equal to 0, if you don't already know, 0 factorial is equal to 1. So this does work for all integer values of n, so positive integers, including 0. Yeah. Well, we would go into the Laplace world. Yeah. So the thing is, so if we say we have a simple differential equation like y prime is equal to t or something like that, to go into the Laplace world, you know now the Laplace of y prime equals the Laplace. Oh, there's a few more things that we should probably mention about the Laplace transform, and I'll mention that in a minute. But you would take each of these things to the Laplace world, and you know now that the t goes into what? 1 over s squared, right? But this is still a little bit of a question mark as to where the derivative goes. And with differential equations, of course, we're going to need to know that. And that's covered in a little bit later on. So once we can take derivatives into the Laplace world, then we can figure out what to do. I suppose we can try to figure out what derivatives would look like in the Laplace world. But before we do that, let's talk a little bit more about the transform. So there's an important piece of information that will allow us to work with a lot of the equations that we've been working with. And that is the fact that the Laplace transformation is a linear transformation, which means that the Laplace of a sum is equal to the sum of the Laplace, and the Laplace of a scalar times the function is the scalar times the Laplace of the function. So those two important properties comprise the idea that it's a linear function or a linear transformation. And derivatives and integrals are all linears, and we are taking integrals using the Laplace transform, so it would be kind of natural that it is a linear transformation. And this will allow us to be able to deal with the types of functions that we've been dealing with. What is not true is that the Laplace transform of a product is not equal to the product of the Laplace transforms. Okay. We might need to deal with things like this, and so we need to introduce some more ideas behind this this idea that we can just multiply things. All right, we have a bunch of we have a table of Laplace transforms available for you. We have the basic exponential function. We have the sine and cosine. We even have the hyperbolic functions here. These hyperbolic functions are really just a combination of a bunch of exponential functions put together. So I don't expect you to memorize this, but it would be good to derive one other one on your own by hand, and then you can check your work to see if you did it correctly. All right? People seem to be leaving early. So if you guys want to go, go. I'll make kind of some announcements after you guys leave. Still talking. Okay, so guess I don't need to record anymore.